Welcome to Ready to Derive. In this lesson, we will learn about the chain rule, one of the most powerful derivative rules in calculus, and one that will enable us to take the derivative of composite functions. Is that composite or composite? I'm not quite sure. Although I am American, I grew up in England, so I'm just very confused about what's what when it comes to pronunciation. So be prepared to hear both. So what is a composite function? Here we go. F of g of x is a composite function. So up until now, we've only been able to take the derivative of f of x. But what if there's another function that's input to f, and that in this case is g? Well, how do we deal with that? Well, we have this chain rule. And why is it called the chain rule? Well, you could use an analogy of a bike chain or chain link fence, but I like kind of the gear mechanism analogy to help. So imagine that X is the white gear, and as you rotate that white gear, it's going to have an effect on G, the green gear. It's going to have a differing effect, so the speed of the white gear is actually going to be different from that of the green. And in turn, the green gear, as that rotates, is going to have a differing effect on the orange one, which is F. So this visual is not quite realistic because all three gears have the same number of spokes, and so actually wouldn't work because they're different sizes, but just work with me here. So in effect, a slight change in X sort of causes a chain reaction, makes a little bit of a change in G, which in turn affects F. So anyway, with that analogy, enough of a preamble here, let's get started. So just to sum up where we are in the calculus series, these are the derivatives we are so far equipped to find. So we have rules for each of these. So let's run through these quickly. By the power rule, the derivative of x cubed is 3x squared. Rad x, let's see if we write that as x to the half. The derivative is half x to the minus half, which is, if you simplify and put it as a radical, is 1 over 2 rad x. That's actually a shortcut that's or a rule that's worth remembering. I mean, I know it's the power rule, but if you can think that the derivative of rad x is 1 over 2 rad x, if you can go straight there, you'll save yourself a lot of time in future derivatives that will involve the chain rule. Okay, the derivative of e to the x is e to the x, sine x is cosine x, ln x is 1 over, and this one down here is another power rule application, negative 1x to the minus 2, which is 1 over x squared. But here are some derivatives we are not equipped to find. So I've taken all these functions on the left here and replaced x with x squared plus 5, as you can see. And what I've effectively done is created a composite function, which is this. I've certainly got f, I'm cubing x squared plus 5, I'm square rooting x squared plus 5. I'm basically inserting a new function into f rather than just x, a sort of more complicated function. So these are composite functions, and we are not equipped to find them yet because, in fact, the chain rule will help us answer these. But in the meantime, there is one that we could find right now, and it's this. Looks like the power rule might be involved, but we can manipulate this, get it into power rule ready form, and actually take the derivative. So the one derivative we can do is this. But we first must get it into what I've termed power rule ready form. And that means that you have to express it as the sum or difference of power functions. So every term has to be of that form, ax to the n. So let's do that. Multiply it by itself 3 times, and if you distribute out, this is what you'll get. So for the derivative, we can now apply the power rule to each term. So that's 6x to the 5th plus 60x cubed plus 150x, and the derivative of the constant 125 is 0. And now let's factor out what we can. So 6x comes out of there, x to the 4th plus 10x squared. Sorry, there was 150x there. I left that behind. And so if I factor out 6x from there, I get 25. And that's 6x let's factor this. X squared plus 5, it looks like, times x squared plus 5 should work, which is 6x, x squared plus 5 squared. So you might already start to see some patterns here. So for example, we had that, it was to the power of 3, and now it's gone down to the power of 2, as you would expect in applying the power rule. But it's not kind of clear, the 6x, not quite clear where that came from. So I'm just going to rewrite this as 3x squared plus 5 to the power of 2 times 2x. And then maybe you can take a moment and try and sort of figure out where that 3 came from and where the 2x came from. So if we take this one step further, so I'm going to color code this now to kind of help you see what's going on. So there's our original function, and here's our derivative. And I particularly want you to see that the orange function, sort of the sort of overview function, is cubing, right? So the orange function is you're taking whatever the input is and cubing. So notice what happens. In fact, the derivative of what I will call the outer function is actually just the power rule. So it's 3 times whatever is in the inside there squared. And then the derivative of this 2x here will come, so this x squared plus 5, we know that this is the inside function. So I'm going to call that, this is the inner function. And so notice that the inner function stays intact. So you take the derivative of the outer function, but you keep the inner function here, x squared plus 5, intact. So what about that 2x? Where is that coming from? Well, perhaps you've already realized that 2x is the derivative of the inner function. It is the derivative of x squared plus 5. The 5 goes away, and the derivative is 2x. So what we just demonstrated in the previous slide was an example of how the chain rule works. Now, it just doesn't work for, it's not just when there's a power function on the outside. It actually works for any combination of functions. So if you have a composite function, h, which is f of g of x, then h prime is just f prime of g of x. Remember, that's the inner function. We just keep that intact. So that's g of x. We could keep referring to it as the inner function, and f is the outer function. And so, so f prime of g of x times g prime x, the derivative of the inside function. So I'm going to put that in words. It's kind of helpful to think of it like this because the notation can get a bit confusing. So the derivative of a composite function is equal to the derivative of the outer function with the inner function as its input times the derivative of the inner function. And in the next slide, we'll get plenty of practice with this. So let's revisit the derivatives that we are now equipped to find thanks to the chain rule. So it was all those composite functions. And to help us execute the chain rule, I'm going to provide this structure, which is really useful. If you identify these 4 quantities, then plugging into the chain rule is very easy. So here's the chain rule just as a review. And the green function is supposed to be the inner function, and the orange is the outer. Now, what makes an inner function an inner function? Well, here it's pretty obvious that x squared plus 5 seems to be on the inside of the radical. And another way to think about it, though, is the inner function is always the first set of things you do to x if you wanted to evaluate the function. So if I wanted to evaluate this function when x is 4, I'd have to square 4 and add 5. First, complete that before I take the square root. So the square root kind of comes after the inside is figured out. So that's f in this case is a square root, and g in this case is x squared plus 5. In fact, g is x squared plus 5 throughout all of these, just to help you sort of see the pattern. And g prime, therefore, is just 2x. So what's changing for each one is actually what the outer function is called. So in the first one, the outer function is the square root of something. Now, I'm not going to put x in there because if you put x, if you were to write f of x equals the square root of x, trust me, that can get you into trouble because you'll forget to put the function g back in. So let's keep that open like that with the open parentheses. So the derivative of the square root, as we learned in the previous slide, is 1 over 2 times the square root. So according to the chain rule, the derivative of the square root is 1 over 2 square root. And then I have to take g of x and plug it back in there. So that's x squared plus 5. And then multiply by the derivative of g of x. And you can tidy that up, cancel the 2's, etc. But I'm going to leave it like that so you see the basic structure. So for the next one, so as I explained before, e is the outer function. So I'm going to write e to the something. That's the outer function. The derivative of e to anything is e to that thing. So the derivative of e to anything is e to it. Put the inside function, the inner function back in, and multiply by the derivative. There, again, it can be tidied up, but that's the basic idea. So in the next one, I know it's going to start to feel a bit repetitive, but it's good to see and good for you. At any moment, you can pause and practice yourself. So the derivative of sine is cosine, open parentheses. So let me go get ready. So here's the cosine waiting for its new input, which is x squared plus 5 times the derivative, 2x. What about ln? So we know the derivative of ln is 1 over. So let's get rid of this first. And let's go back to here. So the derivative of ln, keep that open parentheses, is 1 over that. So it's going to be 1 over. So this is a little tricky. You want to make sure that what goes on the bottom is g. So it's 1 over x squared plus 5 times 2x again. And finally, for the last one, 1 over x squared plus 5. So this one here, remember again from the previous slide that so the overarching function is 1 over, and the derivative of 1 over, say, x, so this is really just a power rule, is 1 over that thing squared. So let me put -1 over something squared. That something is x squared plus 5, and the derivative of that is 2x. So let's practice finding the derivative of a much more complicated function using the chain rule. I'm not going to provide the same structure I did in the previous slide. You can do that for yourself for each portion. So I'm going to start with this one. I will color code for you, but we'll go straight to the results. So the outer function is ln, and the derivative of ln is 1 over. And the inner function is secant t, so I'm going to put 1 over, keep the inside function intact, and then I'm going to multiply by the derivative of secant, which is secant t tan t. And then let's take the middle one. So the outer function is, so let's put minus, the outer function is e. So the derivative of e is e to whatever, and keep the inner function intact, and then multiply by the derivative of the inside function, which is -2. I know I say inside and inner, outside and outer. I'll go interchangeably between the two, so forgive me. And this, let's get this into a kind of power rule ready form, because we do need to write that to the -1/2 in order to be able to do this properly. So the derivative of the outer function, -1/2, according to the power rule, is 1/2, whatever, to the -3/2. The inside function is t squared plus 4, and the derivative of the inside function is 2t. So now we can tidy this up. We will notice, oh, conveniently, that it looks like the secant t's are going to cancel. So we'll get tan t. So let's f prime t equals tan t. And then if we tidy this up a little bit, we'll get 2e to the -2t. Here it looks like the 2's cancel also. We have a minus. And let's just put things back where they belong. So the t is on top here. And it looks like we have the square root on the bottom, which is the square root of t squared plus 4, but now we got a little cube going on there as well. And that's the final answer. In all the practice we've done previously, we've only had to execute the chain rule, but you will find many situations in which you have to find the derivative of a function that will involve both the chain rule and product or quotient rules. So if we look here, we have these two functions multiplying together, so we have a product rule. So we will do the product rule first, and then we will do the chain rule within that. So here's the product rule right here, and then we are going to set up the structure here to help us organize. So u is, let's make u 2x minus 1 cubed, and v will be 3x plus 5 to the 4th. So u prime, now we have to take care of the chain rule. It has to be applied to go from here to here. So it's going to be 3 quantity squared, that's the outside function, times the derivative of the inside function is 2. And tidying that up a little, we get this. Similarly for v prime, 4 times the quantity cubed times the derivative of the inside function, which is 3. And that leaves us with 12 times this quantity. So now we can apply the product rule. So the product rule says u prime times v, so that's 6 times 2x minus 1 squared times 3x plus 5 to the 4th, plus, and then uv primed. So that's 2x minus 1 cubed times 12, 3x plus 5 cubed also. Often you can just leave the derivative unsimplified, unless you're going to actually use the derivative to analyze a function, in which case it's better to sort of factor out and simplify where you can. So let's look for some commonalities between these two expressions. So we notice there's a 6 there and a 12 there, so we can definitely factor out a 6. So I'm going to put the 6 out there. And then if we look here, we have 2x minus 1 squared, 2x minus 1 cubed. The most I can take out is 2x minus 1 squared. And finally, 3x plus 5 to the 4th and cubed. So the most we can take out is this, cubed. And that leaves us with some stuff in the inside. So we have that plus there. And let's go and put in, what factor are we missing in the first expression? We are missing an extra factor of 3x plus 5. And in the second, we're missing a 2 because we factored out 6 from the 12. And we also need an extra factor of 2x minus 1. And so if you finish writing that out and then simplify the bracket, we get, if you simplify that, you will get 7x plus 3, and that's our final answer. So the chain rule can be extended, so not just to deal with the function of a function, but a function of a function of a function, etc., and so on. So we're going to take the case where we just have f of g of h of x. And it's important here to understand which is the outside function, the inner, the middle. What's pretty straightforward, that f is the outer, g is the middle, and h is the inner. Of course, it's a bit less straightforward to identify those in certain combinations of functions, so we'll practice that. And the extended chain rule is kind of the same idea. You start with the outermost function, f, you take the derivative of f prime, and you keep everything else intact inside that. And then you work your way inwards. So then you take the derivative of the middle function, g prime, keeping h of x intact. And finally, you get all the way in to the inner function, and you just find h prime x. So the best way to understand this is really just to do some examples. So let's take this one here. So we have, this one is easy to identify. So because everything's in order. So f is the outer function, g is tan, and then h is this 3x. So if we start with the derivative of the outer function, ln, the derivative of ln is just 1 over. But we have to make sure we put all the rest of it back in there. And then we times by the derivative of the middle function, which is the derivative of tan is secant squared. But don't forget, we've got to keep its input intact. And finally, we multiply that by the derivative of h, which is 3x, and the derivative of 3x is 3. And that's our final answer. And this can be tidied up a little bit. 3 secant squared 3x over tan 3x. Right, and then let's have a look at another example where it's not so obvious as to what's the outside, inside, and middle. So it's better to rewrite this sine squared x as sine x squared. And then we see that, so what is the, start with the inner function. So what's the first thing that's done to x? If x was pi over 4, what would you do first? You would take the sine of it. After you get that answer, you would square that, so that's going to be g, and the outermost function is actually e, so that's f. So once again, the derivative of the outer function, the derivative of e to anything is e to that thing. So I'm going to put sine squared x back in there, times the derivative of the middle function, it's squaring, so it's going to be 2 sine x to the first, and then the derivative of the inside function, sine x, is going to be cosine x. And we can sort of tidy, we can't really simplify that, but you can tidy it up a little bit. 2 sine x cosine x times e to the sine squared x. So we're going to end by looking at an alternative formulation of the chain rule using Leibniz notation, and recall that the derivative in Leibniz notation is dy by dx, very similar to delta y over delta x, so giving a sense of slope, as opposed to notation, derivative notation in function notation. So here we go. If y equals f of g of x, and we know that the chain rule starts by taking the derivative of the outer function, but keeping the interior function intact. Well, that's cumbersome to say, so why not just replace the interior function, the inside function, with u? So let u equal g of x, and then we can redefine y as f of u. So the chain rule in this notation becomes this, which is sort of a quite simple and actually quite beautiful, because notice that if you cancel the du's, or you can't really do that, but if you were to look at that, dy by dx, you'd get dy by dx equals dy by dx. Of course, canceling it then removes the whole idea of the chain rule, but it's nice to show that you can think of dy by dx as being replaced by the product on the right. But where does that product come from? So dy by du is y is just f, so dy by du is just the derivative of the outer function, keeping the inside function as if it was its own variable. And then it's times du by dx. Well, du by dx is just the derivative of the inside function, g of x. So it makes sense. It makes even more sense when you do an example. So we're going to revisit an example from the beginning of the video, y equals sine of x squared plus 5. So you can compare and contrast methods. And we start by saying, well, let u equal the inside function. So u is x squared plus 5. And that means I can rewrite y as sine of u. And then I take the derivative of those with respect to their variables. So the derivative of sine u with respect to u is just cosine u. There's no reason, nothing to worry about, not about the inside function or anything like that. Du by dx is 2x. And then, so with putting this into the chain rule above, dy by du is the first part, so I'm going to put cosine u in there, times du by dx, which is 2x. Now, that's not much use with u still in there, but why not, since I know what u is. We made u to be x squared plus 5. Why not replace that, and then put the 2x, and there we have it. It's not any easier or any more difficult than the other formulation of the chain rule, but it is a nice notation, you know, when you get like sort of a composition of 3 functions, because you can just
keep expanding it. So dy by du, then du by dv, times dv by dx, and you can introduce as many compositions as you like. So it's a very convenient notation, but it's the same principle. So we'll end with one final example of the chain rule using Leibniz notation. So let's take this function and let's define everything. So the u is going to be g of x, or the inner function, and we see, remember, that's the first thing that's done to x. So the first thing, if I was to plug in x equals 2, would be to cube it and multiply by the ln of it. And then only after that would I raise that to the e's power. So y is going to be e to the u. So dy by du, well, that's easy. That's just e to the u. Du by dx, we have something. You need to pause here and think about it because it's not so straightforward. We have a product here. So if we have a product, we're going to, let's make this f and let's make this g. So the product rule says the derivative of f times g plus the derivative of f times the derivative of g, which is 1 over x. That simplifies to 3x squared ln x plus x squared. It would be even more convenient if we just factor out the x squared and we get 3 ln x plus 1. So now let's bring up the Leibniz notation version of the chain rule, and we see that dy by du is just e to the u, and du by dx is that, I'm just going to write du by dx for a moment and I'll write it all out once I replace the u with what it's actually equal to, which is x cubed ln x. And then I can multiply by du by dx, which I found to be this, x squared 3 ln x plus 1. And it's customary, so this is dy by dx, to kind of tidy things up a little bit by always putting e or sine x or cosine x, any of those at the end of the expression. So we are going to write it like this, and that's our final answer. Now, in all this treatment of the chain rule, what I've neglected to say, but I will say now, is this rule only applies if f and g are both differentiable functions. Hopefully that's self-evident.
And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and or subscribe to my YouTube channel, Ready to Derive. Thank you.